subsessions. The session WS2A will focus on ports, railways, and freight corridors. It will be moderated by Anurag Sachan from Dedicated Freight Corridor Corporation of India. This session will be held in this hall. The session WS2B will focus on airports, energy, and telecom. It will be moderated by Luke Brown from Emergency Management Australia and Henriette Bredst from the European Commission. This session will be held at Aftab Mehtab. The session WS2C will focus on water. It will be moderated by Katrine Bruback from 100 Resilient Cities. This session will be held at Diwan-e Khas. When we conclude this session, we'll break for tea and reassemble here at 3:30. I now request the chair and speakers for other sessions to please proceed to the designated halls in case they are here. Other participants may choose to attend the session that interests them the most. Over to the chair now.
Good afternoon, ladies and gentlemen. It's always very tough task to give a presentation just after the lunch. Anyway, I'm grateful to the organizers to give me this opportunity to showcase a flagship project of Indian Railways. So, gentlemen, I'm talking about Dedicated Freight Corridor of Indian Railways, which is a flagship project costing about 13 billion US dollars, funded by JICA as well as World Bank. Basically, I'd like to cover a little history of the Indian Railways, because our audience is also very thin. By the time I think audience will join. Oh, you are also here. Okay, right. So, Indian Railway is the fourth largest railway system in the world after US, Russia, and China. We have a network of 115,000 kilometers of track. We run 22,000 trains every day, and we carry 1 billion tons of traffic in a year. Our network basically is a golden quadrilateral connecting 4 metropolitan cities in India, that is Delhi, Calcutta, Chennai, and Bombay. This golden quadrilateral carries about 60% of the total traffic, which I have told you about 22,000 trains and 1 billion ton traffic. So it carries almost 60% of the total entire traffic. So it's highly saturated. At the time of independence, India had a network of about 50,000 kilometers, and we used to carry about 85% of total freight traffic in India. But somehow we lost this traffic because we were not developing ourselves with time, and now we are carrying only 35% of the traffic. The remaining 65% is going by road network. So this was a big loss to railways. Although, if you see from the environment side, road transport is much more hazardous for the environment compared to the railways. If you see in terms of gram carbon dioxide emission, the emission in railways transport is half of the road transport. So it is a very efficient, energy efficient system, but we lost it because we failed to develop our system. So what action we have taken, I'll just cover it in my presentation. So these are the two legs of the golden quadrilateral. On the north is Delhi. If you go further north is Ludhiana. So the blue line is the western corridor, which is extending from Delhi to Mumbai, that is JNPT. It is about 1,500 kilometers long. And on the right side, it is eastern corridor, which is extending from Ludhiana on the north and passing through Kanpur, Mughal Sarai, and right up to the Sonnagar in Bihar. It is about 1,800 kilometers. So put together both the corridors, it is total kilometer is 2,800 kilometers. It's a double line, fully electrified, automatic signaling. It's a very modern kind of track. And We have provided all kind of safety systems so that no hazard takes place in this system, and the traffic moves seamlessly in this system. See, these are just some highlights that the total corridor is about 2,800 kilometers. And these corridors are passing through 9 states in a country and passing through 62 districts. So it was a huge task to acquire the land, because the line is passing through Bihar and Uttar Pradesh, Haryana, Rajasthan, Maharashtra, Gujarat, so many states. So it was a huge task to acquire about 10,000 hectares of land, costing about 20,000 crores. And total earthwork involved is about 23 crores cubic meter. So you can just imagine, if you do this kind of mega project, so how much harm you make to the environment. So what action we have taken, I'll further take you to that. And in order to have so many rivers across the alignment, we are constructing about 4,000 bridges. Out of that, about 500 are major bridges on very major rivers in India. And besides that, the total track linking of about 6,000 kilometers involved. Now, these are some special features of the project. On the left side, you can see that the present Indian Railway rolling stock. The standard rake at present on Indian Railway carries about 5,400 tons of load. Whereas on the western, this dedicated freight corridor, when it will be completed, will be using heavy haul and long haul. Our trains will be about 1,500 meter long, and it will be carrying 13,000 tons of load. So if you, and the line capacity of these two corridors is about 120 trains each way. So there is a tremendous capacity has been created in these corridors, so that the traffic which is moving in by road, and there is so much of traffic congestion, everybody knows about it. So some of the traffic, which is bulk traffic, will come to the railways, and our highways will be free from that. I'll just show you how we are doing the work. So these are, the entire work is being done by automatic machines. This is a new track construction machine, which is handling pre-stressed concrete sleepers. Every sleeper is 300 kg weight, and the rails are also laid mechanically. We have about 10 such machines, and every machine is doing 1.5 kilometer track every day. So we are linking almost 15 kilometers of track every day. For the electrical works, these are the overhead electrical foundations. This is also being done fully mechanically, so that we don't disturb the environment while doing the work. There's another machine which is, because these are electrified lines, so total 6,000 kilometers of copper wire. It's like a rod over the track, which is to be laid. So this entire overhead electrification is done by these wiring train. This one train itself can lay the wire for a length of about 7 to 8 kilometers in a shift. Once we do such kind of mega projects, it has a great impact on the environment. So whatever initiatives we have taken in this project, we'd like to share with you. This is a study by, I think, World Bank. This study on temperature rise, global temperature warming. So you can see on the y-axis, there's a temperature, and on the x-axis is the year. So you can see that up to year 1900, there was hardly a variation in temperature. It was just plus minus 5 degrees centigrade was the variation. But after 1900, because of the global warming, in the year 2000, and there is an expectation that by the year 2100, the global temperature will increase to 3 degree to 5 degrees centigrade. 3 degrees is a conservative estimate, and 5 degrees is a very, this thing. If we don't take any action to save the environment, this will be the global warming and this will be the increase in temperature. And whatever projects we are doing, infrastructure project, whether it is a railway project or road projects, we have to take care of this temperature increase, because whenever we construct a project like we are constructing a railway project, which will have a life of at least 100 years. See, these are the hazards, the year-wise. You can see that because of global warming, from the year 1950 to 1960, there were 13 incidents of extreme weather events. You can call it, whether it is earthquake or whether it is flood or high wind or precipitation. So there were only 13 events were there. And if you see between 1990 to 1998, every 10 years, it was events were increasing. And now in this last decade, there were total 72 events. In fact, I remember one in the year 2001, 26 Jan, there was a huge earthquake in Bhuj. You must be aware of that. It was 7.7 or Richter scale, where the entire Bhuj was devastated. Thousands of people died. And I just want to share this story because railway was the first one. Because Indian Railway was, in India, it came in 1853, when the first train ran from Mumbai to Thane. And we have a very solid system of disaster management. So I just want to tell you, when the roads were blocked, and it was not possible even to go on foot. So railway was the first one to repair our bridges, and we took the first relief train to Bhuj. This is a very good diagram. This is showing that there are some hazards, which we can call it primary hazards. You can see on the left top is rainfall, which is one of the primary hazards. The second is high temperature, which I have already told you in that because the global warming temperature is rising. And then strong wind, that is also one of the hazards. And the bottom, you can see the earthquake. So there are four primary hazards, and these primary hazards lead to secondary hazards, which is shown as landslide and the flooding and chokage of drain, etc. And that leads to secondary impact, because all your electricity lines and communication line, everything gets disturbed. So that is a secondary impact. So there is such a huge impact of these four major factors, which is not in our control. Now, what we have done in our dedicated freight corridor to handle these hazards. Since World Bank is also with us, and World Bank is a sponsor here also, so World Bank has fixed up one consultant, that is JBA Consulting and SECON, and all the stakeholders were taken into in the study, like RDSO, then Indian Meteorological Department, Central Water Commission for the floods, and National Research Institute of Earth and Sciences for the earthquake. So, and Disaster Resilience System, Japan. We followed the methodology by first defining the critical parameters. It has been identified. That is, fog is also one. In the North India, fog is a very, very severe this thing which affects the rail transport as well as air transport. And the temperature variation is a very serious issue, especially in the North India, and the floods. Now, all these factors were analyzed by our consultants. And we have also studied the international good practices followed in other countries. And then all the disaster risk factors have been screened, and strategy have been finalized that how we'll take care of these various disaster factors. Now, in order to take care of different hazards like extreme temperature, we have analyzed that how much temperature will increase in next 100 years, and whatever instruments or systems we have provided, whether it is track, signaling system, or communication system, everything has been designed. See, we have taken good practices of international practices, but we had to make a lot of changes because of the temperature increase in our country. So we have designed our systems to take care of that increase in temperature. Extreme precipitation and flooding, this we have a lot of experience because Indian Railway has so many bridges, about 60, we have 60,000 bridges, and we have a history of almost 100 years, so we know how to take care of those bridges. We have provided, there is a very robust system of inspection of bridges, then all those railway affecting tanks on the upstream side, we study those, we also inspect that so that no disasters take place in this. And another is sea level. There is a study that the sea level also will increase in future from 0.6 to 0.8 meters. Fortunately, so far dedicated freight corridors are not passing through any the coastal area, so this particular aspect is not affecting us. Storms. So that has also been taken care of during the study, that if any storm takes place. I just want to give an example. In my earlier assignment, I was in charge of a project. It is in Jammu and Kashmir, Udhampur, Srinagar, Baramulla rail link, where there is a river Chenab, and we are constructing there a steel bridge, which has a total 30,000 metric ton of steel. And this is going to be the highest railway arch bridge in the world with a height of 359 meters. So it's a huge bridge, which is going to be a signature bridge in our country. So we have taken all the factors into account while designing this bridge, whether it is earthquake, whether it is a high wind. We have designed this bridge for a wind speed of 266 kilometers per hour. And all the factors have been taken care of this. So we have designed our structures like that. And earthquake is, of course, we have a very robust system of designing all the structures for the earthquake, because our line is passing through zone 5 in India, which is very, very earthquake prone. So we have taken care of this factor also. This is just a comparison that there are 5 factors on the axis scale, that is precipitation, flooding, earthquake, wind, and temperature. On the left side, there is a table which shows the recent variability and changes, recent at present. And in future, you can see that a lot of factors has become, in the bottom you can see that the green color is low risk, no action is required, and the yellow color is potential risk and need more information. So at present, some factors are there which doesn't need any action to be required, but in future we have to take care of this. So while designing our project, that is dedicated freight corridor project or major bridges, we take care of these factors for designing. Now to take care of these factors, what we have done in dedicated freight corridors so that we can run our trains efficiently. So like in order to take care of fog, because in fog all the trains get delayed and there's a huge problem. So we have gone for ATCS level 1 signaling system, because it's not a high speed, otherwise we would have gone for ATCS level 2. But ATCS level 1 is sufficient because it has a automatic system that is a train protected warning system, where if train goes, if driver cannot see anything, he can still go at a speed of 100 kilometers per hour. And there is a system available. If there is any problem in track or signal is not green, then automatically the brakes are applied. So it is very safe. As far as temperature variation is concerned, when we lay our track, we take care of the factors that during summers, the temperature, rail temperature goes as high as more than 50 degrees Celsius in India. And during winters, it goes minus in the north area. So we have designed all our track to take care of this temperature variation. In all our major bridges, we have provided sensors so that if there is any flooding is there in any major river, automatically in the operating control system, all those information will come so that we can take a corrective action. We have a very close coordination with CWC, Central Water Commission, for the flood forecast. And all the flood risks have been assessed, and action taken, because we have a very good system in the railways that we keep all those equipments and material ready before a rainy season. We have a very fixed system that as soon as the monsoon comes, entire Indian Railway, we have a system that somewhere the boulders will be stacked, somewhere the some emergency girders will be kept properly loaded on the wagons, so that if any thing takes place in any railway line, immediately the help is extended to those countries. And there is a very robust warning system is there. Now, this aspect is also very, very important for the environment, that is greenhouse gas emission. So the complete study has been conducted to see that what are the existing factors which is creating greenhouse gas emissions and how it can be controlled. So entire study has been done, and that is the reason that entire dedicated freight corridor is has been provided with electrification, which is a very, very energy efficient system. We have a system of 2 into 25 kVA traction, so that we can run heavy haul trains with a 13,000 tons of load, which is very, very energy efficient, so that we can reduce the GHG as much as possible. This is the scenario. The blue column, it shows that if we have not provided dedicated freight corridor, this would have been 116, would have been the total emission, greenhouse carbon dioxide emission. It is in tons. And when we construct the dedicated freight corridor, it will be reduced by 2.5 times. Then it will become only 47.5. Similarly, on the other corridor, it will be reduced by 6 times. And total saving of carbon dioxide in next 30 years will be 457 million tons of carbon dioxide equivalent. Now, in order to make our system more energy efficient, we have also given a study where when the driver runs the train, the skill is very important, how he applies the brake or how he accelerate the locomotive. So the study has been done, and there also we will have the system in place where driver will be trained how he should run the train so that it is energy efficient. These are the various measures which we have taken so that we avoid any kind of disaster in our system. Like our entire 2,800 kilometers of track is fully welded, one end to other, continuous welded rails. And we have provided re-railing ramps before and after our major bridges, because we cannot afford to have any kind of derailment over the bridges because they are disastrous. And height gauges have been provided on all our under bridges. There are so many roads which is passing through our track. So height gauges have been provided so that any road vehicle should not damage our bridges and under structure. And the design of all the structures have taken care of seismic, hydrological, wind forces into consideration. Our line is passing through some wild animals, forests, etc. So we have also taken care of that in order to save the wild life in our country. Animal corridors have also been planned so that animals like elephants or other they can cross our line safely. I'd like to share some photographs of a project which can show that it's a very, very robust kind of system we are making it. There's one of the completed section where you can see that a bridge has been constructed and an entire embankment has been provided with the complete pitching so that there is no deterioration to our formation. This is another very important factor which we have taken care of, that when the rolling stock moves on the track, all kind of instrumentation have been provided in track so that we know that what kind of stresses are coming on track, and if there is any defect on the rolling stock, that also can be passed on to the operating control center, and we can take a corrective action so that no disaster takes place. This was the inaugural run on 15th of August. We have run first trial train in Western Corridor. So you can see that this locomotive is also looking like a tricolor. This is another section on the Eastern Corridor. We have constructed one very long span bridge for two lines on the top, and the trial train is passing over that. There's another bridge where I think below is the expressway, and we are passing our railway line on top of it. These are our station buildings. These are operating control centers, because we will be handling total 2,800 kilometers of track on the eastern and western sector. So we have provided two operating control centers. One is in Allahabad and another is in Ahmedabad. All these are like war rooms where each and every information about the train running or any emergency or disasters, everything will come here, so that the reaction time for attending those any eventuality will be very, very less. This is another major river where we have constructed a bridge. Thank you very much. Small presentation. Thank you. Gentlemen, pardon me because I have a very urgent meeting at 3 o'clock, so I have to leave, and I request Supriya to further take the session. Thank you.
Thank you, sir, for your presentation on reflecting on DFCCIL's experience on building resilience for the Eastern Freight Corridor. I'd like to invite Florian Hofstetter from SBB in Switzerland to present the Swiss experience of the railway sector. Thank you.
So, welcome. I'm going to talk about risk-orientated natural hazard measurement at the Swiss Federal Railways. Shortly, the agenda. I'm going out the SBB in general, natural hazards in general, natural hazards in the early days, risk-orientated natural hazard management right now, and what are the new challenges in the future. So, the SBB, since 1999, it has been a special stock corporation whose shares held by the Swiss Confederation and the Swiss cantons, so it's kind of half private. We have around 30,000 employees, and we have 14 people which are in the natural hazard team, 6 in the strategy technical part, and I'm one of this, and 8 in the inspection, monitoring, and maintenance team, which are more outside looking around what's going on. We operate around 3,000 km track. We are the biggest operator in Switzerland. And a third of it is exposed to gravitational natural hazards. And most of it is water. Natural hazards in the early days. You were not really aware of the connection between the various hazards. So you had like the rockfall team and you had the water team, but you did not really speak with each other. You also did not have systematic maps, and the importance of maintenance was really underestimated. So you actually just run behind the events. The 1980, 1990, this is around was a big step. There was this flooding, 1987, a big flooding in Switzerland, and there not only the experts, but also like the public could see that it's impossible to guarantee 100% safety. So there was an enhancement of risk-orientated approaches. And since then, we also created hazards map with the extent and the intensity of every hazard. And since 1991, it's also within the law. There are also guidelines and recommendations were carried out, and another big thing is we really want to learn from events and monitoring systems, so we do every time detailed analysis of it. Risk, you know what risk is. We have hazards, exposure, and vulnerability. We're going now through this risk. Risk management can be very good described with a cycle, and it goes with what can happen, what is allowed to happen, which is the acceptable and the unacceptable risk, and what should be done. We go now through all these steps. First, what can happen? I show you this image here that you see that we have how we did the risk calculations in general. We looked at the exposure and the vulnerability at SBB. Here, focus on personal risk, which is kind of a passengers per day or tray frequency. On the other side, we had water, rockfall, avalanche, all the hazards. And then we just intersected and calculated the risk with a software which was carried out by the government and a lot of experts, and then we adapted it to ourselves. And as a result, we got then a map, as you will see. If we just look a little bit more in detail how it looks like, we have, for example, looking at rockfalls, we just did a large-scale rockfall modeling, and then we took out the relevant rockfalls. And then we combined these somehow, so we merged these trajectories. And there we could say these are the tracks with potentially rockfall risk. On the next slide, you will see here the exposure and the vulnerability. So at this certain track, we added the exposure and vulnerability criteria, which is like people a day, people per train, train speed, train lethality, and so on. And as a result, as you can see, is there like a map where you can see where we have, looking here at the individual risk, where we can see high risk or low risk or what kind of risk we want to see. And on the left side, we see without protection structures on monitoring systems, and on the right side, we see the same map with protection structures and monitoring systems. And you could also see that there's no high risk anymore. So we know that our protection structures and monitoring systems work. Then, next step, once we know where the risks are, we also have to say what is allowed to happen. And for this, we have these protection objectives. We're looking at the individual personal risk, the collective personal risk, and the availability risk. At the individual personal risk, we looked at the acceptable rate of causality to a hazard, which is 1 over 100,000. And this is 10 times higher than the average mortality risk in Switzerland. So it's like a statistical value. And then for the collective personal risk, we monetize it by 10 million Swiss francs per prevented death. And once we have a part where we can say that the value of this part is greater than 10,000 Swiss francs per 100 meter per year, we look a little bit closer at it and see if we can do something. And availability risk, we protect actually everything against the 100-year event and sometimes even against the 300-year event. What are the benefits if we do so? We have a presentation of the total founding requirements on the SBB network, as you can see in the background. And also risk hotspots became apparent. Furthermore, there's a comparability across the entire railway network, so that the left side is do the same as the right side. And we can calculate the economic efficiency of measures like the benefit costs. Yeah, what should be done then? We have all kinds of protection structures and monitoring systems. We have large-scale ones with satellite and laser, as you could see in the morning, and small-scale ones which are like telejoint meters or cameras. But sometimes we say it's better to alert than instead of building. So alert systems often are often more the cost-effective solution than physical shoring. And also, it protects against the very, very large and rare events, which you almost not can build something. And we say it's a reduction of the risk of train collision by 90%. As this image shows here, we still have a net or something, but it's more like a carrier system for this alert system instead of a real protection structure. One part of this whole risk-oriented management is the integral risk management, which says all hazards must be looked to or must be considered together. And also all responsible parties must participate in the planning and implementation of measures. Looking at this image here, there was a flooding which affected the road, the railways, and the villages. It would be very stupid if we just made or build a protection dam for the railways and not talk to the roads and to the village. And so also we want to say that all types of measures should be included. What are the new challenges? Here I'm showing a new map where we see a potential risk from surface runoff. So surface runoff is kind of not something really new, but due to this dry land we have right now, it comes much more than before. So now it's kind of a new challenge we have to deal with, and we also now have some new risks. Looking more in detail, what are the new challenges on the hazard side? We have, also Switzerland has climate change, and there we have the crater extent. We have new scenarios. This is what I show you somehow before, something which not really happened that much before. We have new places. We have change in annuality. We have a resistance of a hazard. So once it starts to rain, it just rains like a week instead of just 1-2 days. And it occurs in other than the typical seasons. For example, mud flows. I'm used to have mud flows during July, June when we have these more rainy days. But now also because in winter, the snow is much higher and below its rain, we also have sometimes mud flows connecting together with an avalanche in the middle of winter. But still, we still should be prepared for events which might not occur that frequently anymore. So we still could have snow in altitude. So we should have this in our focus too. What are the new challenges on the exposure and vulnerability side? We will have higher terrain frequency. We will have more people. We have faster and longer trains. We have new tracks, and probably there will even higher security needs of the population start. So we have to change our protection goals. Looking here at Zurich, how we have, for example, the train frequency right now, and then how it's going to expand in the future. What are we doing against this? We're doing monitoring and we have early detection. We do a lot of research, knowledge, and developing know-how. We also coordinated with all kinds of parties within the SBB and outside. For example, we have a close contact to the passengers transport department for the exposure and vulnerability facts. And we already organize resource needs, and we organize financing for the countermeasurements for all these new challenges. And then we have ongoing projects where we see new hazards modeling methods, and we also develop prospective scenarios. What are the conclusions of this talk I just had? For a risk-oriented natural hazard management, following has to be known. You have to know the hazards with the extent and the intensity. You have to know the exposure and the vulnerability. And you have to know your protection objectives. And these ones are not static. They change a lot of time. So you also have to adapt it for the future. Furthermore, integrated. We have to look at all hazards together, and we have to combine all effects together. And also, in many places, an alert system is more cost-risk effective than protection structures. So, but unless the availability must always be guaranteed. So, thank you, and I wish you a trouble-free journey.
Thank you, Florian. I'd like to invite Dr. Shoichi Hashimoto to present. Dr. Hashimoto is the former director of the National Railway Research Institute in Japan, and he currently consults on several projects for JICA as part of Tonichi Engineering Consultants in Japan. Thank you, sir.
Change the glass. Thank you very much for giving me the opportunity to presentation today. Former, I was a director of research institutes and professor of the technical college. Nowadays, I belong design of East-South Asia Railway project by JICA. This is my presentation agenda. The first, technical cooperation for existing lines. There are two examples, Vietnam and the Philippines. And second, countermeasures against disasters of railway in Japan. Japan Railway opened 150 years ago. The history of 150 is the birth of the railway operation and the disaster. The third, new railway project in Philippines, application from Japan. Now I belong to this project. This is Vietnam National Railways from Hanoi to Ho Chi Minh City. The length of 1,700 kilometers. There are bridge, 300 bridge, many bridge. Then we replaced long old bridge, 44 bridge safety improvement project, already finished. Brown color is the old weakened bridge. This bridge older than 50 or 60 years. Light blue bridge is after replacement. And in same time, the both side track is improvement. 44 bridges, total length around 6,500 meters. And approach track of both side bridge is the length 45,000 meters was improved. Then before this project, express train took 36 hours from Hanoi to Ho Chi Minh City. Now, after this project, it took 24 hours. This Tap Chan Bridge is a final our construction replacement bridge. Right side, the Vietnam diesel locomotive, just after the finish this project. Well, next, this map showed existing Manila, Philippines in the city railways. There are 4 railways, LRT1, LRT2, MRT3, and Philippine National Railways. The first stage of LRT1 is ODA from Europe. And after the renovation and the new train came from Japan. Now we are designing ongoing LRT1 extension, LRT2 extension, and MRT3 rehabilitation. I belong to this 3 projects. And next, recent, I take a photograph by myself, Philippine National Railways. The track and vehicle condition is not so good because there are a few maintenance. This is a diesel locomotive of Philippine National Railways. That is a trailer for passenger. Came from Japan. That trailer is electric car in Japan now, Philippines, pulled by a diesel locomotive. By the way, Japan has suffered a lot of earthquake damage from the past. We have many experience. We have a hazard large earthquake every year now. Design standards have been repeatedly revised many times. Then our structure is stronger and stronger. That is a Hanshin Awaji earthquake. Then huge earthquake in the ocean caused huge tsunami. Trucks along the ocean suffered catastrophic damage. Now the location of the new route has been moved to the hill. This is the early detection system against huge earthquake. Emergency brake apply before seismic waves reach the truck. Before secondary strong wave to catch preliminary tremor. This is we used in Shinkansen high-speed railways over 30 years. No dead, no injury for passenger. Over 50 years, zero. Next, in Japan, we suffered every disaster. The storm caused the train to overturn. Driving criteria have been revised from many experience. Weak soil structure was damaged by heavy rainfall. The design standard for soil structure have been revised, of course. The embankment became stronger and stronger. Now I belong to the designing and planning team of JICA. There we are designing this railway we called North-South commuter railways. The first stage, the center area around length 37 kilometers. Design work is already finished. Bidding is now ongoing. Second stage, north extension from north extension, north side of Manila, length around 51 kilometers, and south extension design ongoing. Last week I went to and stayed Manila this project. The total length 140 kilometers. Then we plan and propose Philippine government weather monitoring sensor, the arrangement weather monitoring sensor, seismometer, rain gauge, anemometer. The signals can be displayed on the facility monitoring console in the operation control center room, and same time recorded in the storage device. This map arrangement of weather monitoring sensors, I decide the position of weather monitoring sensor by myself. there are many sensors along the track. We have a two-stage classification seismic design. We called level 1 moderate earthquake and level 2 severe earthquake. Just slight difference to design method. We use our design method to construct new railways in Philippine project now. And in earthquake occurred, there is necessity of inspection for resumption of train operation. For example, seismic intensity scale in Japan, 3 or less than 3. Inspection is no need. Quick resume to operation. But intensity scale 4 or more than 5, we sometimes inspect the track site. Of course, when convert to other country intensity scale as necessary. This is one example of wind speed criteria for train operation. When the wind speed has get stronger, train operation is suppressed in Japan. When the wind speed exceeds the difference value, the commander in OCC instructs all drivers to stop. Operation shall resume when the wind speed decreases. This is a compression forecast of bridge in North-South Commuter Railways, North Extension area. Almost design work is finished this April. The next, next stage, bidding. Thank you for your attention.